Alright, we have our last section of the whole year, 14.1, linear regression. We're going to be testing it. So first we're going to review some stuff. The data below are the temperatures randomly chosen during days of summer class and the number of absences during those days. So we have our list. So first thing we need to do is either put it into the Inspire, label them, whatever you want, A, B, or GeoGebra. We got to put them in our spreadsheet. Doesn't matter what you do. Alright, now we're going to find a linear equation that relates temperature on those days with the number of absences. So first, we need to make sure that we have our y hat, it's predicted times something x plus our intercept. And we want to tell what those are. Y hat is the predicted number of absences, and x is the temperature. And I probably want to be specific. So either way, just to review, we have our data in here. You go to a different page, calculator page, menu, calculations, and two variable, linear regression. Either one of these will work. Same thing. Our lists were A and B. Don't need anything else in there. So we have our M, we have our B, we have our R squared, and our R. All things that we need. If we're doing this on GeoGebra, you highlight your columns, two variable regression analysis, analyze. I've already been doing stuff, so we need a linear model. Here's our equation, should be y hat, and statistics, so we can get our R, and we'll have to find our R squared. Oh, R squared's right there. So we have all the data that we need. So going back to our problem. Our equation is 0.4485x plus, actually not plus, it's minus 30.267. What do those values mean? Well, our slope, 0.4485, means as x increases by 1, so x is a temperature in Fahrenheit, as the temp increases by 1 degree Fahrenheit, the number of absences on average increases 0.4485. So if you want to multiply that by 10 degrees to get 4.4 absences, or whatever the case may be. Now, what does our y-intercept mean? It means if x is 0, that's our y value. So if temp is 0 degrees Fahrenheit, we would have negative 30.26 absences. Of course, that makes no sense in this situation. Although if it was 0 degrees Fahrenheit in the middle of the summer, I think we would have tons of absences. Linear correlation coefficient. Remember, that is our r, our lowercase r. It is 0.98. There is a 98% positive linear correlation between temp and number of absences. Coefficient of determination, yes, coefficient, not coefficient. I'm not Homer Simpson. So r squared, now it's capitalized, but it's the same thing, 0.96. We can say 96% of the total variation of our y, of our total number of absences, is explained by the temperature. 96%. 4% is explained by other variables. Maybe the teacher sucks. Maybe the school sucks. Maybe they just don't want to go to school because school's boring. I don't know. But we know 96% of the total variation in the total number of absences is explained by the temperature. So that's just a little bit of review. Now, if we're moving on to our new stuff, we have section 14.1. Last section we're going to do, and that's it. Is inference or statistical testing of our least squares regression line to see if there actually is a correlation. So using the data that we had. So again, remember our equation is y hat. Instead of m and b, we use b1 and x and b naught. b1 and b naught are statistics that come from sample, from our data. And really the only thing we're interested in is our coefficient of x. Our b naught is not our issue here. That's not what we're looking at. We want to test if beta 1, the parameter of b1, equals 0. Really, we want to put this into beta 1x plus beta O. Now, we're not going to talk about beta naught. Run the test. You need to do several things. First thing, just like always, simple and simple. And two, the residuals have to be normally distributed. So of course that's done by normal probability plot or normal quantile plot. Either one will work. We've done those before. So now, unlike last chapter, we have three different options. Two-tailed, we have left-tailed, and we have right-tailed. Again, our null is the same for all of them. It's always an equality. It's always dealing with our parameter. Has not changed, will not change, does not change, do not change it. So beta 1 equals 0 for all of those. Obviously, our alternate here is that beta 1 is not equal to 0. All that's saying is we have linear correlation. Don't care if it's positive, don't care if it's negative, that's what there is. Because if beta 1 equals 0, there's no correlation. Our left tail is we have a negative correlation. And if we have, that means beta 1 is less than 0, it's a negative number. So we have a negative correlation. One is right tails, beta 1 is greater than 0, so we have a positive correlation. And of course, these are all linear correlations. We're not going into quadratics. If we keep looking at some other stuff we need to look at. We need to figure out what kind of distribution we're using distribution. Our degrees of freedom is our sample size, so the pairs minus 2. Obviously, we need alpha still. They'll tell us that. If not, we use 0.05. Our test statistic, T naught, is just like everything else. It's our point estimate. It's our parameter divided by our standard deviation. That is, in this case, our point estimate is B1. Our parameter is beta 1. And our standard deviation is SB1. And we'll talk about that more in a little bit. It's written different on the calculator. And of course, we're going to use our calculator to cheat and do all this. And remember that beta 1 is really 0, so that doesn't really do anything there. So all we have to do is kind of plug this in the calculator, get our data, and start doing something. All right, we're going to do an example here. We have height versus head circumference. Pediatrician wants to determine the relation that may exist between child's head height and head circumference. Hopes that's not true because my daughter has a giant head. She randomly selects 11 children from her practice, measures their heads and heights and head circumferences, and we get the following data. I believe we've used this data before, but we're going to use it again. Treating height as the explanatory variable, x, determine the estimates of beta naught and beta 1. All that's asking for the linear regression line. So again, we do what we've done before, except now we're using different data. Two variable analysis, analyze. We got our equation. Again, it's y naught, or y hat, sorry, not y, because it's our predicted. We have our r value of 0.9143. We have our r squared value, if we scroll down, of 0.836. We can do the same thing on the calculator. I believe I labeled those H and C. So we do the same thing. And we got the same value. So nothing different. Maybe a little bit different. And I guess this is backwards. But either way, we get what we need. And we can even dot and see our residuals. I'll see how far off they are. All right. First of all, we just need to write down our equation. Y hat equals 0.1602x plus 15.82. Compute the standard error there. Okay, that's when we need to run the test. But first, before we do that, let's get our hypothesis. So beta 1 is 0, always. Now we just have to see if it's greater than or less than. So if the residuals are normally distributed, test to claim that linear relation exists between. So it's a two-tailed test. And now we have to check if they're normally distributed. So going back here, from standard plot to residual plot, there's not really a pattern. It looks pretty normal. And if we go to hidden statistics, it'll let me. We have H, C, and of course we do our norm probability plot's not going to work here for whatever reason. We have to do regression first. Then we can do, nope, we're not doing that either. We will have to come back to that. I don't know. So residual plot. And then we get our normal probability plot. You can see that they're pretty close. It's a little bit different than what we've done before. All right. More bad? Yep. Simple random sample. We said randomly selects, normal, yes, because we checked it. And we need to keep on moving with our hypothesis. So it's a two-tailed. We need to find our B naught is our beta 1 divided by our SB1. Now we need to find those. Well, we have B1, it's up here. And we need to find our test statistic, our p-value, and all that. Well, the calculator and GeoGebra does that for us. So I'm not quite sure that GeoGebra does do that for us. Our calculator, however, does. So I'm going to double check my data here. It is agency. So go to menu, test, and we're doing linear regression t-test. H, then C, and we want two tails. And we have everything that we need. We have our A, our B, which, if you scroll up, is actually part of our equation. Our B is our beta 1. So B is 0.1827, slightly different. I might have typed in the data wrong. Our beta naught is right here is an addendum for our GeoGebra friends. To find our standard error of the slope SB1, GeoGebra doesn't give it to you. We'll have to write to them, start a petition, get something going, but we have to use this formula. And I will give you this formula on the test because I don't think that's fair if you don't have the calculator. So it's the square root of the sum of the standard error here, 0.0819, divided by n minus 2, the degrees of freedom, which in this case, we had 11 samples, so it's 9, divided by the square root of the standard deviation of the residuals of x, is what that is, so 11.9773. That'll give you our SB1, our standard errors, 0.27561. So to find our T-score, we have to do our beta 1 divided by SB1. Our beta 1, 0.1827, divided by 0.27561, gives us our T-score of 6.3. And then we have to take it old school, doing our either TCDF or obviously we can go back over to our probability, a distribution, P distribution, or student distribution, degrees of freedom, 9, right, this is two-tailed, but because it's positive, we use right, we put in our 6.63, we need to get more rounding, like 0.05 times 2, it'll give us our 0.001, like we expect. So that's the way we're going to have to go do about it. Unfortunately, you got to do it this long way to find the standard error of the slope. Alright, sorry about that. No, we cannot do this on GeoGebra, so the Inspire is the way to go. The data that we need is our SE slope, which is SB1. We need our SE, our standard error of the mean. And of course, well, we have our T-score of 6.63. We even have our p-value. Very, very low, 0.0096. So let's see if we can see where all that comes from. So our B1 was 0.1827 divided by the standard error, SB1, or what it says standard error of the slopes, 0.02756. If we go back to our calculator and we divide those two, 0.1827 divided by 0.027561, and that is exactly what our T-score is. A little bit off because of rounding. And if we want to find our p-value, the long way, statistics, distribution, and a TCDF, our lower bound, now our lower bound is our t-statistic because it's positive. So then 9, TE 999, degrees of freedom. We had 11 and minus 2. We got 0.48. A little bit different than what we had. Oh, it's different because we got multiplied by 2, which is 2. So we have our p-value, and we can write our conclusion. So this gives us our t-score, like we said, of 6.63, which on the calculator gives you its probability not greater than, because it's a positive value. It's approximately 0.00096. Of course, we compare that to our alpha, which was 0.5. So that is true, so we reject a no. So what does that mean for our conclusion? It means we have the same way we did before to reject. Ergo, we can support the claim that there is a linear correlation. If that's beta 1 not equaling 0 means that there is some kind of correlation. There is a coefficient there. There is a linear correlation between head size and height based on our sample at alpha equals 0.05. So we have the same parts, test statistic, our p-value, reject, hypothesis, we had checked for normality, we had our hypotheses, we had our equation here. We answered all these questions. Actually, our alpha level was not 0.05, it was 0.01, which does not change the fact that we rejected because it was very low. All right, a child comes in for a physical, the determined his height to be 26.5 inches, however, child is gaining rather confidence in the nerve is unable to measure the height circumference. What would be a good guess to that height circumference? Well, what do? We plug in 26 into our equation. This equation does pretty much work. So we go back up to our equation. Y hat equals 0.1602. Actually, that was the incorrect one. I did type in the data incorrect. It should be 0.1827. And our A is 12.4932. So you got to make sure you type in the data correctly, which of course I did not. So it is our slope, 0.1827 times whatever their claim is for the height, 26.5, times or plus our y-intercept, 12.4932. So they should be 17.33, or their head size to be 17.33, given our data. So 7 times 26.5 plus 12.49. Again, about 17.33 inches. And what's our y variable? That is our head circumference. It's kind of hard to measure a baby's head. So we have everything that we need here.